This kind of started with the image of Israel Tau that was released in 2015. So it was the first image at a very high resolution with ALMA. And they actually picked this target simply because it was bright. They didn't think that there was going to be substructure in it. It was just, let's see how this disk looks like at high angle resolution. And then they found this amazing substructure. So this is kind of how it started and how it's going. We now have many disks that have been observed at high angular resolution. So there's the D-sharp, which was a large program with ALMA where they observed 20 disks at high resolution to reveal substructure. And there are also more and more observations available with these transition disks, so disks with inner cavities that also even show these asymmetries. So we simply have dozens of disks now with high resolution observations that we're trying to make sense of. So just to repeat what we talked about this morning, what's the origin of the dust rings? We think that all of these dust rings and asymmetries are essentially dust traps. These dust traps are a way to prevent the radial drift from happening. So they were already proposed long before they were actually observed. They were initially proposed as a way to halt the drift, to get some kind of substructure there. And that means that, and then the way to generate them is either in the form of a radial pressure bump, for example, at the edge of a planet gap, or in the form of a vortex due to the Rossby wave instability of such a radial pressure bump, where the instability leads to these large-scale vortices that we also saw this morning. And yeah, just as a reminder that these two are not protoplanetary disks with ALMA. Have you guys seen these images before? Yes. Good. So these are the images taken with the Event Horizon telescope. Look at the scale. This is 50 microarcseconds. So this is really a factor of thousands smaller than whatever we observed with ALMA. So these are essentially this is the ionized gas surrounding black holes in both Sagittarius and AIM. And the angular size is actually 10,000 times smaller than a typical.
Those are the same scale?
Yeah, because one is much closer to us.
Yeah.
But the angular scale is separate. Yeah. Okay, so in terms of we have different types of substructure, and the first one I want to talk about are the large inner cavities, or the transition disks. I've recently written a review paper about this. You can find it on the archive. Much more information, but I want to spend a bit of time because historically these disks were the first where we could see that there was a gap structure, and this was actually because of the spectral energy distribution. So if you remember how the spectral energy distribution of a disk looks like, we have the flux as function of wavelength, we have the contribution from the star, and then we have the infrared excess from all the essentially different dust radii in the clustering radii in the disk, all emitting at slightly different temperatures. So you have a superposition of black bodies here in the infrared excess. And then if you would carve a gap in this would naturally lead to a deficit in the infrared part of the SCP. So the first transition disk was actually discovered in 1989. And in particular, the Spitzer space telescope that was able to observe many disks in the infrared, in particular between 5 and 35 micron, which is where we usually find this dip if it's present. The Spitzer found several dozens of these SEPs that had that signature, and many of the transition disk candidates were essentially selected in that way. So some of those were followed up, some of the brightest ones were already followed up with these early readings interferometers, revealing that there was indeed a gap in the dust distribution. But this was mainly just confirming that there's really a gap there. It didn't really reveal anything yet about the origin of this cavity. So, as I mentioned, Spitzer has transition disk candidates. And what's interesting with SED selected transition disks is that even a cavity of 2 astronomical units can already be visible in the SED, because remember, you're talking about the very warm dust very close to the star. As soon as you remove a little bit of that, you immediately get that deficit. And then it doesn't really matter if it's 2 AU or 20 AU. Obviously, only those largest cavities could be confirmed with millimeter interferometry with those early interferometers. In the literature, you will see that there are so-called color criteria to select transition disks. So this is mostly a way to, instead of staring at SEDs and kind of, yeah, that kind of looks like one, yeah, maybe that's one too, maybe. So that's not very consistent, right? So what people usually do is you have like a table with all these flux points, all the SEDs, and then you say, well, I'm dividing this flux point by this flux point, that is essentially a color, and then if the color between these 2 wavelengths fulfills this criteria, then the SED probably has this kind of shape. So in that way you can essentially automate the process and do it consistently for a larger sample. However, there are multiple color criteria which are not sometimes overlapping and sometimes are not, so there's a bit of inconsistency there. It's good, mostly because everyone started to develop their own favorite color criteria. Well, also if you want to analyze these SEDs, if you want to derive cavity size, for example, from an SED like this, you will find that it's complicated because you have to correct for extinction. You have to worry about edge on disk, because an edge on disk would also block part of the star. There are all kinds of radiative transfer effects in the helium. So the SED analysis that you could find in the literature is, yeah, take a bit of a grain of salt, because there's often multiple ways to interpret these data. But something that was discovered back then, so when we only had SED transition disk candidates, was that many of them were actually still accreting. So whatever was carving the gap, material was also still going through onto the host star. That was very important. So if we now go talk about the origin of these cavities, and I'm going to talk about this from a historical perspective, kind of what were the possible explanations that people had back then. Well, first of all, there was the idea of a binary, so that or actually circumbinary disk. Obviously, if you have 2 stars orbiting each other, they will truncate the disk from the inside. And it actually turned out that one of the early transition disks that was found, called Tau 4, SED is this, you can see over here, a binary companion was found in 2008. Another transition disk, what is our images, with an even larger cavity, was also found to be binary. So there's at least 2 cases where, where the transition disk can be explained by binarity. However, for many other transition disks, binarity has been excluded. So, yeah, there must be something else carving the gap as well. Another very popular explanation was photon evaporation. Because you remember, and we talked about this morning, that when the accretion and the gas surface density drop below a certain level, photon evaporation clears a gap at a few astronomical units, and then that gap quickly expands. So maybe when we're observing transition disks, we are observing the moment, like we're capturing the moment that they are in the process of dissipating, in the process of clearing. However, there's many studies about this topic. It seems like the majority of the transition disks, at least these large transitions with cavities of more than 20-30 AU, cannot be explained by photon evaporation because their accretion rates are essentially too high to be consistent. And so we can see that in this plot, and there's multiple versions of this plot with slightly different models. So the accretion rate as a function of inner wall radius, inner cavity radius, and only what the area in gray, those are potential transition disks that can be explained by photocoagulation. As you can see, there are many data points out here, so large cavities, high accretion rates, they're simply inconsistent. There's no way that photocoagulation is above that accretion rate and can actually have clear together. So again, large number of transition disks cannot be explained by this scenario. Then there was another interesting proposal, and this was for the transition disks that were found by their SED. So the idea was that, well, if you have a disk that is where all the dust has drifted inwards, and then in the inner part of the disk it has grown to larger sizes, maybe your growth is so efficient, your fragmentation is so limited that you're removing all your small grains. So you get a dip in your SED simply because there are only large grains in the inner part of the disk. And this was proven to be true with dust evolution models by Marel et al. But he also showed that you cannot actually grow further than millimeter sizes. Or essentially, even if you grow to like boulders or planetesimals, you would still grind down to some level to millimeter particles. So you would never see a gap in a millimeter dust distribution. So it was an interesting scenario to explain some of the SEDs with a gap, but it definitely cannot explain again the millimeter images of some of these transitions. Interestingly, in a very recent paper of mine, I found a couple of disks that were very compact in millimeter emission, but that also have this dip in the infrared. So these are probably examples of disks where indeed all the dust is drifted inwards, and the smallest grains have been removed, and only the larger particles remain. Okay. So with ALMA, we have imaged, so kind of getting out of the historical overview. With ALMA, we've now imaged many of these transitions to much better detail than in previous years. And this is an overview of this dust cavity, more than 20 astronomical units. Other than cavities, we've seen now that there is actually a lot of variety in structure, so we can have a cavity, or a cavity with an inner dust disk. You can also have a cavity plus an outer ring. You can have an asymmetry, maybe a combination of a ring and an asymmetry, maybe clumps, or like asymmetric clumps along the ring. There's many variations. We think that they're all pressure bumps. And so my question to you now is, how do we know if a dust structure is a pressure bump? What do we need to look at in order to confirm that? We're not talking about whether there's a planet there or not. It's like, how do we know that the millimeter dust ring is a pressure bump? Sorry? Yeah, but so how do we know that there's a gap in what? Like that, yeah. Anyone else? The density of what?
Of the disk in the dust.
Not necessarily, but yeah, that is somewhat true. But it's actually not what I mean. Do you remember that I showed these 3 panels from TWR Hydra, where you saw the 12 CO emission and the dust emission? I said, yeah, here we see evidence of dust transport. We see that the dust is more concentrated than the gas. So for dust traps, it's actually the same story. You want to compare the dust concentration with the distribution of the gas. So here are 2 examples of transition disks with radial trapping and azimuthal trapping. So now on the left we have the millimeter dust distribution. We have this narrow ring, this narrow asymmetry. We have the gas distribution from 13 CO. So we also see a gap that is smaller than in the dust. So that makes sense because the dust ring is at the very outer edge. And we have the small dust grains that seem to kind of follow the gas as well. And so it's really, particularly in the azimuthal case, this is very clear. The dust is much more concentrated than the gas and the small grains. So this is the segregation between large grains and gas and small dust. That is what proves that trapping is there. And so, like a very famous example of that was, of course, the Iris 48 disk. This was, I think, in 2013. One of you presenting on Friday. So this was actually the first time that we found observational evidence for dust trapping. Before that, it was proposed in dust evolution models. But yeah, the dust images itself were not enough to prove it. You needed to have the combination of the gas emission and the dust emission, and that was what we had here. So we had the asymmetric millimeter dust, the gas showing primarily this ring, and we even had some infrared images showing that the small grains were also showing essentially a ray shape. And so this is the distribution that we interpreted from that. Large grains concentrated on one side, gas and small grains distributed throughout, possibly caused by a companion inside the inner gas. And what was actually so interesting about this discovery is that these kind of asymmetric pressure bumps were predicted even before we had these predictions of radial dust rates. So these are, okay, I guess the references dropped out. No, okay, so the references are actually listed here. So there's this paper from Bart and Somalia from 1995 and Cloud and Henning 1997. So these are both from the 90s, long before we had ALMA or even millimeter images of transitions. And they already said, well, you know, through some instabilities, some hydro instabilities in the disk, you can get these large-scale vortices. And as soon as you have a vortex, you will trap the dust, and then maybe that will be the starting point of planet formation. So this was already proposed long before we knew about, you know, transition disks or anything like that. Okay. So I already mentioned this segregation between large dust and gas and small dust. And so we improved the pressure bumps. So I want to look at a little bit more detail at some of these transition disks. So what we see, this is a sample of 4 transition disks. The dust continuum is shown in blue, and the integrated 13 CR is shown in red. And as you can see, in all of these cases, the gas is located still inside the cavity, and the dust ring is sort of at the outer edge of that gas cap. And this is consistent with something that essentially drops, like the gas surface density drops gradually inside, and only at the very outer edge, at the very maximum of this surface density profile, that's where the pressure maximum is, and that's where the dust rate is. So essentially, this the observation of the gaps in the gas are evidence for planet, and that you don't have something else that creates the pressure bump, because then you wouldn't have this kind of depletion in the gas. So with the image that I was showing, we also tried to quantify that. So basically, using a thermochemical model, so something that models the temperature and molecular abundances in the disk, that I'll talk more about tomorrow. You can actually try to estimate, like, what is the gas surface density that reproduces this kind of 13 CO emission. Like, how, if you have a surface density profile and a gap, how deep does the gap have to be in order to be consistent with the observations? So for all these 4 disks, we actually found pretty deep depletion of 1, 2, or even 3 orders of magnitude. And if you compare that with planet disk interaction simulations, so the surface density is a function of R, here is the location of the planet as the result of a planet carving a gap. we see that several orders of magnitude means that you're talking about several Jupiter masses of planets that must be responsible. So at least for this transition disk, yeah, there must be very massive planets. This initial analysis was This initial analysis was rather simple. You see that these are profiles that are not physical. They're just meant to sort of parameterize the gas surface. That's the steep drop off. In later data of another disk, we got dust materium, the 12CO, 13CO, and C18O. These are more and more optically thin, and the fact that their gap size became that inner gap size became larger if you go to more optically thin emission means that you must have a gradual drop in the gas surface density. And we're actually able to model that shape of the gap directly by looking at these CO data. So, and something similar was found in the 16 tau disk. Also here, you essentially have different cavity sizes depending on whether you look at 12CO, 13CO, or C18CO. And also here, they were able to model this with a more realistic planet card gap. Yes?
Sorry, I have a question. In previous slides, and also on this one, I don't have very clear because it says that you don't use the gas for the CEO AstroTwinCoLO. So do you filter like only that one because that's the information we need, or that's the only thing we can image like that?
It's the same. So CO AstroTwinCoLO is the best tracer we have for gas surface density.
So we filter it and we only look at that, and we the other ones, like the other gas %.
So can you use filter?
Just like getting this CO, and let's say there's another element, like H or something like that. We just look at it. I just don't.
Oh, okay. So the problem with hydrogen, the H2, is that because it's a symmetric molecule, it doesn't have a dipole moment, and therefore it doesn't have molecular transitions in the millimeter, like rotational transitions. So there's we cannot observe H2 with almond. And then the next most abundant molecule is CO. So that's it. And then after that you have even other molecules. And also CO is tricky, and I'll show that tomorrow, right? CO is still very tricky, but this is kind of the best we have. Okay, then another cool thing that we discovered about these transition disks is that many of them turned out to have an inner dust disk. So in the high resolution ALMA observation, we found that there's often this tiny blob in the center of the disk, and also here in some of these images. Also, this is evidence for a planet-cleared gap. So if you would have, for example, a photoevaporation gap, there is no way that the dust would be able to drift through and still create that inner dust disk. So you need to have something that is a somewhat shallow gap where some dust is able to go through to maintain that amount of dust in the air. So why do we think it's planets? I mean, I've given some arguments already based on these, like the shape of these gas gaps, etc. But of course, the best evidence for this scenario is the direct detection of these protoplanets. There are now two transition disks with very firm detections of protoplanets, bound to PDS-70. So we see the near-infrared blob here, kind of a blob here. The second blob was much more clear in H-alpha emissions, which is a spatially resolved H-alpha. So we essentially have two accreting protoplanets inside the dust cavity. So this is the millimeter image. We even have a signal of a certain planetary disk right here that's overlapping with the protoplanet here. And actually, if we look at the CO distribution, we see again the same behavior. We see a gas gap that is well inside the dust gap, dust ring that is consistent with the whole tracking scenario. Then ABO-Rigay is this other disk, so this one is actually somewhat asymmetric. Here there is a blob in the infrared. There's probably some circumplanetary material here as well. but it's definitely robust and it is moving at the right orbit, etc. Also here we have this gas giant. So yeah, this is, at least for 2 systems, we know it's planets, and this makes it a lot more likely that for other systems with similar characteristics that there are planets there as well. However, finding planets in this is really hard because you need a technique that's called high contrast imaging, where you block the light of the star in order to see tiny, tiny dots close to it. Because you have to remember, the star with planets around it is essentially it's like a lighthouse with fireflies around it. So you're trying to look for the fireflies right next to that. You want to have something that blocks this really bright light before you can see those faint dots. This technique was first applied in this system HR 8799. This is actually not a protoplanetary disk. It's already more than 30 mega years old. But we were able to, or Marel was able to find planets with this technique for the first time. The fact that this system is only 40 parsecs away makes it a bit easier as well. Most of the protoplanetary disks that we know, the transition disks that we know, are further away. They're dustier because they're part of this cloud, and that makes it much harder to do anything in the optical. If you go to the literature, you will see many more claims of protoplanets. And often 1 or 2 years later, there's another paper using the same data set or maybe doing a follow-up observation. And then there's that blob is no longer there. So I call those failed detections. And essentially, other than PDS-70 and AB Aurigae, there are no other confirmed protoplanets in the cavities today. And people have tried to put limits on what kind of planet can be present. But it always relies on a lot of assumptions. Like if you don't detect anything, so you have an upper limit, it becomes a lot more debatable what your upper limit is on your mass, because you have to make too many assumptions about how that planet would look like and how bright it would be. Yeah.
You can go back.
Yeah.
Just all. Okay, there.
This one.
Those planets must be massive planets and
Yes.
are so far from the star.
Yes.
Because if you see the scale, for example, in the AB, Aurigae,
Yeah.
yeah,
It's
the
90.
orbital magnitude.
93 AU.
So, do you think the inner side of the disk there are more planets? You can imagine that you can,
In these disks, you mean?
for example, yeah.
There could be, but because of this, essentially because of this mask that you have to put on the star, and then the diffraction around that mask, there is a limit to how close you can get to the star to detect planets.
So you can't see even planets.
Not with current instruments. No. With future instruments, we can. Yeah. That was actually going to be my next slide, so it's good that you asked. That I didn't plan this. So the way that high contrast imaging works, I remember we're trying to measure something very faint next to something very bright. We're always still limited by the diffraction around this mask. But then these are the typical limits that we have in terms of contrast. So we have the flux ratio with respect to the host star, like going down to 10 to the minus 8, to like 10 to the minus 5 or so, as a function of separation. The Gemini G-Pi and the VLT sphere, at least VLT sphere is the instrument that was used to detect the protoplanets of PDS-70b. So they can detect a contrast of about 10 to the minus 5, 10 to the minus 6 at 0.2 arcsecond separation. If you go further out, your contrast becomes better, obviously, because you have less issues with the star itself. The idea of future instruments of, for example, the ELT, which is actually not called here, is to go at least 1 order of magnitude deeper down in this region. But these are the contrast limits that we have now. JWST is unfortunately not going to help for close-in planets, but hopefully the ELT will. And And then this flux contrast is, of course, the brightness of that planet, or the upper limit on that brightness can be converted by certain assumption to a planet. Okay, so I've talked a lot about these transition disks and inner cavities. Now I want to move to these asymmetries. I've already mentioned asymmetries several times. So these are azimuthal dust straps. We actually have detected several of them. It's still not very clear, like why do we see an asymmetry in some disks and not in others. Some are really large scale and high contrast. Others are, relatively small scale. It's just like a little blob as part of a ring. There's even Hydra, a tiny, tiny asymmetry, which you only really see if you zoom in onto the image. It's still kind of an open question why we see asymmetries only in some of the disks. So the main explanation of these asymmetries I've already shown you. This was this idea of a Rossby wave instability that creates a vortex, and the vortex that traps the dust in the azimuthal direction. The problem with this explanation, at least back in 2013 when we discovered Iris 48, is that this Rossby wave instability, or the vortex itself, only survives if the turbulence is low, if alpha is 10 to minus 4 or below. And back then, 9 years ago, that still seemed very unlikely because everyone was still a big fan of this viscous disk model with alpha 10 to minus 2. So essentially, people were skeptical of this explanation, mostly because of this alpha parameter. So there was this alternative explanation that came from another group where they knew from again I think black hole accretion disk simulations that if you have a binary that can essentially a certain binary disk can become eccentric, and then the eccentricity results in a so-called horseshoe. So this is also an overdensity in the gas, but it's not as a result of an instability. It's simply due to the eccentricity of the disk. And in that case, this scenario would also work with alpha 10 to minus 2. However, if all disks are alpha 10 to minus 4 or lower, like essentially if the turbulence is really low in all disks, this may still happen, but it's not like a requirement. So I just want to put this in a bit in historical context of why this was proposed at that time. However, they do have a point because there is one disk that is asymmetric and that we also know to be a binary. And I've mentioned it about 10 minutes ago. Do you remember that one? This disk. It's an asymmetric dust trap. It's known to have a binary companion at about 10 to 20 AU. Like this horseshoe is more like 150 AU. And simulations have shown that you can indeed reproduce this asymmetry in the system without the need for Rossby wave instability, without a low turbulence or alpha value. Okay, then there's something interesting going on in some of these asymmetries, in the sense that they may be somewhat connected to spirals, or maybe they're part of the spirals. So there's this disk. So in the background we see the continuum, the ulnar continuum, and in the white contours we see the spiral arms from scattered light. And as you can see, it almost seems like the spiral arm originates from this asymmetry, or maybe continues into that asymmetry. So here's another example where this is the ulnar millimeter image, and if you enhance the resolution, it's kind of an image filtering technique, it also starts to look like these are actually spiral features. Spiral features in the millimeter. And then the same in this particular disk. And even in this disk, there's a hint of a spiral in the millimeter. And this is also, some of these asymmetries may actually be part of the spiral arms. It's still an open question. It does, however, seem unlikely that this is trapping. And yeah, I posted why, but I think I'm just going to explain it. The reason that spiral density waves, they move through the disk pretty quickly, like they move with the speed of the thing that is causing them. And in order to trap dust, things have to be at the same location for a pretty long time, pretty large amount of time. And the fact that the spiral moves through the disk makes it less likely that millimeter particles are trapped. So you wouldn't see a very high contrast here between millimeter dust and gas. Okay, so I've talked a lot about transition disks. Now I want to talk about more general gaps. So you may remember some of these old images of disks observed at low resolution. They appear to be smooth. And with all that, they turned out to have gaps and rings. HL tau is probably the nicest example here. Right? This is how HL tau used to look like. And now we know that it actually looks like this. Also in this other disks. What we see in high angular resolution is that there are many of these narrow gaps present in dust distribution. And so what's interesting is that these ring disks or gap disks don't have any signature in their SED. So their SED just looks like a full disk. So why is that? Can you think of why there is no gap, no dip in the infrared part of the SED in such a disk?
Maybe it's not hard enough, like the star has not cleared up the dots. So there's excess radiation.
Yeah. Anyone else? So you were pretty close. The point is that in all of these disks, you see that there's still a significant amount of dust close to the star. So, and the infrared part in the SED that is often cleared, that is where you see the dip, that is the very warm dust. If you start to, but here the gap doesn't really start until 30 AU or so. Over there, all the dust is already cold, and the temperature gradient becomes a lot smaller at these larger radii. So removing dust at, let's say, 21 Kelvin, but not at 20 Kelvin, is not going to affect your SED. While removing dust at 200 Kelvin will affect your SED. That's the reason. Okay, so these are just some examples. Then there's the beautiful gallery of the D-sharp survey that I was already showing before. So they observed 20 disks, 0.04 arcseconds. They found, again, a large diversity in substructures, although most of the substructure really are gaps and rings. And then some show a hint of like spiral arms. This one shows a spiral arm. And over here, a clump along the ring. And then also this, there's 163. Okay, here's that dish that had that little wiggle here. So also in rings and gaps, we have a diversity of substructures. With higher resolution, we've also seen in several of these transition disks that the broad rings that we saw before actually consist of multiple rings. So in a way, if we forget about that central part, these disks have some similarity with rings and gaps as well. And yeah, people are actually starting to say that, yeah, we shouldn't distinguish these disks. They're all kind of the same. The transition disks are simply more extreme in the sizes of their gaps. And that may be true. That's still a debate. What's interesting is that we've also started to see rings and gaps in really young disks that are only 0.5 to 1 mega-year old. So the disk is still embedded in the cloud. So here are just a couple of examples of that. So again, transition disks, but also get ring disks. Yeah, this tells us that whatever is causing these gaps, whatever creates them, it must happen really quickly because they're already present at 0.5 million years, or 500,000 years. So if these things are caused by planets, those planets must have formed in less than 500,000 years. And that's really fast for planet formation. So how can we find out what is causing the gaps, dust gaps in these ring disks? If you think of what we did with the transition disks. What do we need to observe? We want to know if these gaps are caused by planets. Well, how did we do this in the transition disks? What was the clue that they were planets?
You check pH of planets for the increase in planets.
Yeah, that's a good point. So you want to look for the protoplanets itself. Unfortunately, that's even harder for these kind of gaps because the planets that carve these gaps are even lower mass than those in the transition disk. I mean, people have tried it, but they haven't found anything, and I'm actually not surprised considering even in transition disks we're kind of on the way. But what else did we observe in the transition disk where I said, hey, this is a signature that must be planets? Exactly, exactly, the gas distribution. We want to look at the CO isotopologues in these disks. Well, we've tried that as well. And there have been several studies, in particular on this disk, 1806-6296. I already mentioned this morning, this is the brightest disk that we know, and it has these beautiful dust rings and gaps. And now we also have CO isotopologue observations. And what they saw when they looked carefully, so here we have the azimuth, these are the moment maps, and this is the azimuthally average profile. And if they looked really carefully, they noticed that there were some dips in the CO emission at the location of the dust caps. So I was like, okay, that's cool. So let's try to, they tried to quantify that with a rather simple model. And they said, well, there are gaps present, but these gaps are, maybe 1 order of magnitude, like a factor of 10 deep in gas substance. In the dust, they may be quite big. In the gas, they were sort of a factor of 5 up to 10 deep. So definitely not as deep as what we've seen in transition disks. However, unfortunately, life is not that easy because in these gap disks, because the gaps are not that deep, there's still a lot of dust there, that is actually going to change the gas temperature inside these gaps. And so I showed in a modeling paper that, so for a gas surface density like this, and then different depletions, different drops in density inside the gaps, you may, if your gap is not deep enough, you may actually have an increase in emission inside these gaps. Essentially, your temperature increases inside the gap because of the lower dust density. And then another modeling paper even showed that, if you look at the channel, you kind of see the backside of the disk as well. You notice that? That this is the front side, and here's the backside. So if you integrate over the whole thing, you start to get contributions from the backside of the disk at the locations of the gaps, and essentially it becomes even harder. So if you get dizzy now, don't worry, I'm still getting dizzy thinking about this. The main thing here is that it's really hard to estimate the gas structure, the gas distribution in ring disks because of these additional effects. Then there is this, there was also a large program with Alma called MAPS, where they targeted 5 disks, also all with rings and gaps, and they observed them in different molecules. And without going into the chemistry here, they essentially found a large diversity in gaps in these various molecules. You can see all these different kind of structures of the molecules. But unfortunately, there was no clear correlation between the rings and gaps in molecular line and the dust container rings. So some of the gaps overlap and others don't. So it's not clear whether these molecules are actually tracing gas surface density variations, if there really are dips in the gas surface density. It's it's kind of a mess, and it's really still really hard to interpret this. Okay. So then to talk a little bit about the origin of the rings and gaps. So of course we like to think that they're all caused by planets. Because we say it's planets and we get more funding because everyone wants to research about planets. That's a joke. Obviously because of the transition disk, it is a very promising observation. Some attempts that people have done in explaining these disks, like these sharp disks with planets, is by hydrodynamic simulations of planet gap theory. So they try to reproduce the widths of the gaps by these planet disk interaction simulations. And then based on that, they fit a planet mass at the location of the gap. And then they actually put that in this big exoplanet orbital radius plot that I've shown in the beginning. And here are the inferred planets from these sharp. So they're basically saying, yeah, these planets are not detectable by current observations, so they could be there. We will just never be able to observe them. This is the population of planets that they propose that is responsible for these gaps. And so something to keep in mind here is that you need a minimum mass in order to clear a gap to begin with, and that is from these type of simulations. You can estimate that. It's an equation. It's called the Pebble isolation mass. That's the mass of a planet that is high enough so that you get a pressure bump that is strong enough that pebbles no longer go inside the gap. So that's why it's called the Pebble isolation mass. There's no longer pebbles passing through. And this depends on primarily on the location of the planet, and a little bit, and therefore a little bit on turbulence, on scale height. Like there's a number of parameters, but this is approximately the mass, and that means that at these typical radii where we see the gaps in ALMA, this is about 10 to 20 Earth masses. And we see this in various simulations, and even though you don't see a clear gap in the gas distribution, you will get a strong concentration of dust at the elevation. You will get this pressure bump, this dust trap that is shown in the rings. I am considering the time here. Yeah. So let me very quickly see. No, okay. I think I'm going to take a break here because we're also sort of halfway in my slide numbers. And so I talked a lot about why planets could be causing these gaps. After that, I'm going to talk about a couple of other scenarios. So let's take a 10-minute break. Yeah, we'll continue 3:05.
Because this is pretty logical.
Yeah, so that's it's so you get and the 12CO comes from the higher layers.
This
It's the same. Yeah. Oh yeah.
So I was already from my house.
Okay. Okay. Yeah, no problem. No problem. Thanks for all your questions.
Eso es entonces ¿qué pasa? Totalmente fácil. Café. Ahora. Pero hasta ahora esto está más equilibrado.
Para trabajar como operador de estas cosas. Sí, pues, me gusta también. Pues, como es de la sí, muy idea de que la matolita. Después crear estos datos, transformar en estas visibilidades. Sí, que es algo adicional, se está viendo, ¿no? Yo me acuerdo con muchas similitudes.
Yes, we're missing a few people, but
Estas ideas son para.
are they outside? Did you see that? Oh, okay, yeah, just that.
Sí, ellos son esos cada uno es de un equipo distinto. Sí, cada uno es. Pues es el mismo, unos datos crudos, cada uno los procesó y todo.
No, la segunda.
Ya es lo que
Yo estaba mirando esa de hecho.
Es la que la mejor.
no.
La que mejor
Sí,
se
la
ajusta según ellos. La que más nos gusta.
You're last one, right? There's nobody else. No. Okay. Oh, okay. Okay, so we've talked a lot about planets causing gaps, but since we don't detect the planets, since it's according to planetary information theory, it's really hard to form planets at this large orbital radii, a lot of other mechanisms have been proposed as well. And so one quite important one, basically after the HL image was revealed, was this idea of snow lights. So what she noticed was that the dips of the HL disk appear to coincide with the freeze-out temperatures of several of the molecules that we are expecting to find in disks. And she thought, well, what if this is not coincidence, right? Like, what if the reason that we see a dip is because grains are stickier at the snow line, right? And because that's where suddenly everything starts to freeze out. And that means that they grow faster. And that way you essentially grow beyond millimeter sizes, and therefore you get a dip in the millimeter emission because you remove some of your millimeter particles.
Sorry.
Yeah.
This snow line can maybe create a pressure pump.
That's also, but that was not the original idea. Yeah. The original idea was much simpler. It was just increased stickiness of the grains. So now for HL, how does it need to work? But then, of course, we want to test if this is true for other discs as well. But before we go to that, let me ask you, how do you determine the location of the snow line? How do you know where a certain molecule freezes out?
With equilibrium temperature for the star, you know that the spectral type is to make equilibrium temperature independent with independence of radius.
Yeah, exactly. So the brightness of the star sets the temperature throughout the disk, the temperature profile throughout the disk. And then we know at what temperatures different molecules freeze out, so we can find the exact radii where the temperature drops below. So very good. Okay, so in a follow-up study, she actually found that for 3 other disks, there was something similar. Like there was clearly a gap location close to the CO snow line in disks. However, when we went to even larger samples, like essentially just collecting all the disks where we had the information about the gaps in the rings, it turned out that there was no clear correlation between the gap locations and the major snow line locations. So here we see this is the radius of the gaps, this is the square root of the luminosity, so this is essentially the temperature. In colors we see is the locations of the snow lines, and we see some gaps overlap, but others do not at all. And interestingly, there were 3 papers that came out within the same month. Mine, unfortunately, so this was December, January, so mine unfortunately became 2019. But that was pretty much at the same time as these other 2. And in all 3 papers, we did a large sample study of different targets, essentially finding that this is not. It may be an explanation for some of the gaps and rings, but it's not like a uniform explanation. You cannot explain all of this in this way. And then finally, I mentioned it briefly this morning also. There are many of these hydrodynamic instabilities, things that happen in the gas, possibly related to magnetic fields, related to ionization, that can create small perturbations that could also create pressure bumps and therefore for dust rings. And so I don't want to go into too much detail here. There are several review papers where they summarize all of these processes, and kind of what they've been trying to show is that there are different processes active in different parts of the disk. So this is scale height, this is the radius. All these different processes are active in different parts of the disk and can create pressure bumps on different scales. It's pretty hard to test them observationally. It's basically only if you can rule out planets and if you can rule out other things, it must be one of these instabilities. But otherwise, it's pretty hard to test them. So, I'm just going to give a few examples. There's one here it's very much in the inner part of the disk. Remember that I told you that the MRI, the magnetorotational instability, probably works in the very inner part of the disk where everything is very hot and very ionized. So there you can have this coupling with the magnetic fields and the MRI is active. But of course, there is a transition to the region where the MRI is no longer active, where the dead zone begins. So at that transition, you would naturally get a gradient in the viscosity, and that would result in a pressure bump, and therefore for dust rings. And so they even simulated that with a future telescope, the NGBLA, with even higher resolution than ALMA, you will be able to see dust rings at this location where you have that MRI transition. So what's the problem with this explanation for our observed gas dust rings that we have so far? Why can this not be a uniform explanation?
Sorry, that connects to the question I was thinking.
Okay.
I heard that maybe like dust is just like homogeneous thing, like it's the same that you can have several compositions of dust, and then in the inner part of the disk you can have different sublimation radiuses for different kinds of dust.
True.
I don't know. That's not very clear to me, so I wanted to ask you about that. Do you observe that in different wavelengths or?
I think so. So that kind of differences you can measure in the infrared, like in infrared spectroscopy, where you're sensitive to essentially different dust compositions. But if you go to ALMA millimeter, you no longer have spectral features of the dust.
So dust in radio millimeter emits like uniformly.
Yeah. But in infrared, you will be able to, and that has indeed been. There are variations from disk to disk, which could be related to what you're talking about, different compositions, different sublimation radii. Yeah, but that's not at all related to this point. But yeah, thanks for asking it. Anytime. Any thoughts? Like, why can we not use this as a way to explain HL tau, for example? We look at the scale of the emission, and we think about the physics. This is a transition that you only have in the very inner part of the disk. As I mentioned, the MRI is only active in this very hot ionized region. So as soon as you go outside of that, you lose this transition. So this is not something that happens on larger scales. So therefore, it cannot explain HL tau. Only dust rings very close in that we haven't even observed yet. Then there is this thing called the thermal wave instability. So this has, the idea here is that if the disk gets heated, that in some angles the disk would essentially puff up, and then you get a shadowing behind it, and that would, because of the instability, that would also get enhanced. And also that would apparently result in dust rings. So this can actually happen at larger scales as well. So here's the simulation shows a dust ring of like 30 AU. This would imply that there's some link between the dust ring locations and the temperature in the disk, which, yeah, so it's kind of similar as the snow line in that sense, that there must be some temperature dependence. We haven't seen that, but it could be that some rings are related to this phenomenon, but it cannot be the only uniform explanation. Then there's still the idea that the dead zone, so the region of low ionization, is not present throughout the disk, that in the outer part of the disk, essentially the radiation of the star, the collisions in dim lanes still provide enough ionization so that the dead zone eventually ends. So there you would have another transition between non-MRI active and MRI active, which would again lead to dust rings at larger orbital radii. Also, this one would be pretty hard. Yeah, you would need to measure the ionization throughout the disk. It would be really hard to test. So I'm just, some people really like these kind of high dynamic instabilities because they can create dust rings everywhere. They may be active in different parts of the disks, but it's without real testable observables, it remains really hard to confirm or essentially deny that and say that they return this. Hopefully, if we have larger samples, like a uniform approach of magnitude, lifetime, relative efficiency of these observables, that means we can actually start to test these mechanisms. Without well-understanding statistics on these properties and also statistics on dust rings, it's kind of hard to claim that a certain mechanism it's a way out if we really can rule out the planets in some of these disks. There are still other ways to create pressure bumps. Okay. So what if we go back to our initial explanation? Can it be planets?
Yes.
Yes. Okay. Yeah. But I was yeah. So why yes? And don't say because of funding.
They are building planets.
They are building planets. So the argument is that because there must be planets being built there must be signature. Okay, that's a good one. I actually want to go for the why not. What are the reasons that maybe it's not planets?
Must be planets.
Don't worry, I'm going to do devil's advocate here. So first I'm going to be very, very pessimistic. First, it cannot be planets because we haven't detected these planets. Because there are not many exoplanets at these large radii either. So why would they only be present in protoplanetary disks, but then not in exoplanet? Also, there are not so many giant exoplanets in general. About 20% of all the stars have a giant exoplanet. And based on all these beautiful images, it seems like all the disks have gaps. Then because of the chicken-egg problem, like you need pressure bumps to begin with to create dust concentrations to form planets. So how do we start? And then finally, because core accretion, so essentially the main planet formation mechanism, cannot explain planet formation at large orbital radii. At least that's what they've been saying. So now I'm going to argue against all of these points. So I'm not saying I'm right, I'm just saying I can argue against all of these points. So protoplanets not being detected, the sensitivity of high contrast imaging is still poor, especially close to the star. We've seen that in that context. Exoplanets in the current population, the planets may migrate inwards. So maybe the planets that are present in the disk that are carving the gaps end up much closer to the star. So we cannot do that comparison one-on-one. This argument that there are not so many giant planets to begin with, only 20%, and all this seems to have gaps. Yeah, that's not entirely true, because we only have high resolution observations of the brightest disks. We haven't really looked yet at the fainter, the smaller disks. So we don't know if all of the disks have gaps. Just the bright disks have gaps. For the smaller ones, we don't know. The chicken-egg problem, so planets may have formed in dust traps in embedded conditions, maybe through some of these hydrodynamic instabilities. And now we're just looking at the remnants of the disk. There's no more planet formation happening. We're just looking at a disk where all the planets have already formed. They've created dust traps, and now the dust traps are gonna, just stick around until the disk is dissipated. Finally, the core accretion, the planet formation models. Core accretion hasn't actually been computed in realistic disk conditions, like the extreme settling, the very low turbulence. The trapping, essentially conditions are very different than in our classical planet formation models where everything was smooth and sort of equally distributed. So I hope this that gives you something to work with. Yeah. Okay, so that's it about my planet speech. Going to move topic a little bit. So other substructures, although. These are still gaps, but now we're talking about debris disks. Remember, debris disks are these planetesimal belts around stars that are more than 10 million years old. So they're no longer protoplanetary, they're not accreting anymore. They're often found around main sequence stars. This is a very famous image of a debris disk from a hut. And also this one here, where we see the dust emission in sort of a ring shape. Also, if we look at the spectral energy distribution, we see that there's some infrared excess, but only at longer wavelengths. So very cold dust, pretty far from the host star. There's no gas disk anymore, and the only reason that the amount of dust that we see can only be there if they're continuously replenished by planetesimal collisions. So in the grid disk, we actually see a large diversity of morphologies as well, also asymmetries, warps and misalignments. We see, of course, gaps, but also eccentric rings and gaps. We see asymmetries, we see clumps. So we kind of see a lot of things there as well. And there's not really a uniform analysis possible yet, because we have a rather limited sample of debris disks. And it's still really hard to say how common debris disks are. So some attempts were done with the Herschel debris survey, where they tried to measure the occurrence rate, or actually the incidence rate, of debris disks as a function of spectral time. So with some sensitivity calculation, like a detection-based calculation, they said, well, the probability that an A star has a debris disk can be as high as 50%, but for FGK stars, it actually drops down to 20% and it goes even down to a few percent for an M star. So there's some spectral type effects. So debris disks are also in general often found around A stars, but that's just because of the brightness. But even if you correct for this sensitivity, detection bias, you find that they are more often more common around A stars. But in terms of substructure in the debris disk, there's really nothing that we can say yet. Okay. So, if we look at the dust masses of protoplanetary disks compared to debris disks, we see this as a function of age. We see that there's this strong drop-off. This was the result in 2008. And this was often interpreted as some kind of rapid dissipation of the disk. So something happens with the dust mass towards the end of the lifetime. However, in my recent paper, I've argued that maybe only the transition disks, the disks that have large dust rings, they are the ones that can create these planetesimal belts. And these are the only ones that become detectable debris disks. And it would make sense because also both debris disks and transition disks are most commonly found around early type stars, higher mass stars. And this was also somewhat inspired by this study, where we looked at the millimeter dust mass as a function of infrared excess. We also see that the millimeter dust mass goes down during the class 2 phase, probably due to radial drift. But then as the gas dissipates, so the infrared excess also decreases, you're no longer tracing the entire population. So the debris disks are the remnants only of these disks that have planetesimal belts, and all these other disks, the ones where the dust drifts inwards, become completely undetectable. So this is just a hypothesis. We definitely haven't proven it yet, but this helps perhaps a little bit in understanding where these debris disks come from. Okay, next, morphology, misalignments. So we talked a little about gaps. Now we also have disks with gaps that are misaligned with respect to each other. So there's a very famous disk, TWD Ori. This is a really fun disk because it's actually a triple star system. The 3 stars are in the center here, and then the disk itself has triple rings as well. So it became a fun story. So based on these images, we're able to derive that the orientation of each of the rings, and including the orientation of that triple star system, is somewhat misaligned with each other. And we think that this is related to some dynamical effect where the disk is broken due to the interaction between the companions with each other and also with the disk. And there's an even more extreme example of that in this system, like Kennedy, where you have a binary system. This is actually a quadruple star system. One close binary here, one close binary here, and this outer thing orbits in the plane of the screen. But then this is misaligned with respect to the orbit of that outer plane. This is called a polar orbit. This is like a 90-degree misalignment. I've been told by dynamics people that this is actually, you either have a very strong misalignment, like a polar orbit, or something that's very close to aligned. That those two are relatively stable. Everything in between will evolve over time and eventually, flip into one of the two directions. So, okay, we had already mentioned this misalignment yesterday, I think. When we saw that in some of the scattered light images, we see the shadows along the dust ring. And I already showed you that this could essentially be explained if the inner dust disk is misaligned with respect to the outer dust disk. So this is all fitting in the same story. Again, it must be caused by some kind of dynamical braking effect, like that there's a companion in here that breaks the disk, and then maybe the inner disk starts to process or gets otherwise disturbed. So also this kind of misalignment is rather common. Remember that in this kind of imaging, this is scattered light imaging, we are looking at surface layers of small dust grains, we're not looking at the millimeters. So this is why these shadows are more easily visible. And here for that scattered light imaging, there's numerous telescopes, Gemini, Subaru, VLT, and Keck, that can all do this type of imaging. So if you go to the review paper reliability, you see a large overview of these scattered light images. And so one of the features are these shadows. You see that many of these is the narrow shadows. There's also a couple of discs where half of this is in the shadow. So they think that this is caused by a somewhat larger inner disk that is tilted. Apparently all of it can be modeled. There's even an example of a shadow disk with these narrow features, where the features are orbiting as a function of time. So these are the data taken 2012, 15, 17, several observations during 2017. And these shadows move as a function of time. So this misalignment may actually change over time as well, which makes it even harder to interpret. Then, other than scattered light, there's another way to measure misalignment, and that is by measuring the orientation of these inner disks directly. And we can do this with VLTI observations. So this is optical interferometry, or near-field interferometry, I should say. So Gero knows much more about that. So with these kind of observations, so these are visibilities. Obviously, they're not as well sampled as all my data, but yeah, this is a visibility signal. Visibility is a function of baseline, which you can interpret as a dust ring at, look at the scale here, milli-arc-second scale. So this is really like 0.5 AU from the host star. There is a dusty ring. And it's actually possible to derive the orientation of that ring really well. And then in one of the studies with VLTI, they did this comparison between this orientation of this inner dust ring compared to the orientation of the outer disk with ALMA. And they even combined that with the shadows that we're seeing in scattered light. Because if you have an inner ring orientation, you can imagine that you can be oriented either like this or like this. It would look the same, right? But the shadows would then be in different locations of the disk. So together with the scattered light images, they will be able to pin down the relative orientation of the inner and outer disks. Well, going back to the scattered lights, of course we also have spirals in scattered light. I think you've already seen these a couple of times. These are a couple of very famous examples, very beautiful double-armed spiral arms. Also there's a bit of a diversity in terms of pitch angle, and sometimes only one arm is visible. Sometimes they're a bit more branching out, sometimes they're very winded up. And also in some cases there's, if you have a companion, there's spiral arms seen as well, but in that case the companion is probably generating the spiral arm. Spirals are also seen in ALMA CO emission. So you don't immediately see this if you look at the integrated CO map. But if you subtract an axisymmetric model image from your zero moment map, you're left with this residual. And in this residual, and also in this one, you can recognize kind of a spiral shape. So the idea is that also in 12CO we are somewhat sensitive to the surface variations in certain spiral arms. Finally, we also see spiral arms in the millimeter. I already mentioned this briefly in the D-sharp discs. And also here, the best way to actually see that is by subtracting some axisymmetric model. And then in the individuals, all you're left with are these spiral arms. And and then finally, we have this comparison. I already showed you. There was this disc that shows a spiral in the millimeter emission, and it actually seems to follow the same sort of curvature as the spiral seen in scattered light. Here, see here in the background in yellow, this is the scattered light, and this is the ALMA. And you can actually interpret this as the emission coming from different heights in the disk. In the millimeter, the emission comes from pretty close to the midplane. In the scattered light, it comes from higher up, but they are part of the same structure. So the spiral arm must actually be vertically extended. So all of this stuff that I'm telling about spiral arms is just, this is what we observe. There is no consistent story yet in how to interpret them. A lot of what people do is just, we report a spiral, we analyze it as well as possible, but the real origin is still a bit of a mystery. So there are two sort of main origins for spirals. One is, of course, the planet explanation again. So if a planet carves again, it also launches spiral density waves throughout the disk, and maybe that's what we're looking at. Also, but as an alternative, here we go, gravitational instability. So fragmentation of the disk, if the disk is very massive, would also result in spiral-like features. The spirals that we see in millimeter are usually associated with gravitational instability, while the ones in scattered light are often associated with planets. But the more we find out about them, the more debate there is about how we can really interpret them. So from what I can see, I would say that the question is still open. It's not fully conclusive. And we're simply trying to gather more statistics and more information. Then a final type of substructure I'm only going to mention are so-called streamers. So these are large-scale structures, mostly in CO, that essentially seem to be infall from the clouds onto the disk. So here, in the very center, here we see the photoplanetary disk. And then we have the large-scale CO emission on this side and also on this side, also in this particular system. And also here the interpretation is that the cloud is still feeding the disk, and we're looking at some component there. But there's only a handful of sources where this has been observed so far. Okay, so we've talked a lot about the different substructures that we have. I do want to talk a little bit now about the detectability of substructures. I also mentioned that this morning, the detection of a substructure is resolution dependent. Many high-resolution images reveal substructure in disks that were previously thought to be smooth. So, for example, this first was smooth for 0.3 arc second, and then later turned out to have at least one gap. If we want to say something about how often substructure occurs, we need to have complete samples, or at least complete representative samples, to say something about statistics. Unfortunately, the only complete disk surveys that we have with ALMA are these snapshot surveys that were taken at low resolution. And only some samples of these surveys were followed up at high resolution. So we don't really have good statistics there. And the transition disks are even worse because some of them were discovered in these low resolution surveys, but some of them were targeted specifically because of the dip in the SED or because they were previously imaged by another imaging interferometer. So transition disks are even more messy. So if we look at the number of disks that are mapped with ALMA low resolution, we're actually doing really well. So there's this, remember this figure of all the nearby clusters. Out to 200 parsec, we have mapped pretty much everything down to this is the dust detection limit. So since 2015, 2016. Most regions have been mapped down to sensitivity of less than 1 Earth mass. This gives the number of disks that have been detected so far. So you can see really this transition between pre-ALMA and post-ALMA. Pre-ALMA, we had very shallow detection limits, only a handful of regions. And in the last 6 years, that's many more clusters have been observed and down to much higher sensitivity. So at least in terms of detecting disks, we're doing pretty well, but we have to be really careful with saying like how many substructures are there in the disks, as long as we don't have the high resolution. And so something very important to keep in mind here, if we look at the disks in Lucas survey, for example, so this is a 0.25 arc-second resolution, half of the detections, and sorry, these two are actually not, but that shape was too complicated. Half of these disks, like all of these disks here, except this one, are unresolved. So they're just a blob, and we don't know how large they are. And you can see that in this size luminosity diagram. So here we have the size of the disk, and here the flux. Over here are all the larger disks. And actually, most of those disks have a large cavity or they're ring disks. They have substructure, we've detected that because we've already followed up with high resolution. But all of these disks down here with lower fluxes, they are unresolved. So we only have an upper limit in their size. They can be anywhere in this part of the world. I'm going to get all my data on these sources. It's actually taken from an accepted proposal for which data will be delivered next year. So hopefully next year I'm going to have an answer to this question later. But really keep in mind that half of the disks are unresolved, which means that they're less than 20 AU in radius and maybe as small as a few AU. So even in high resolution survey studies, but there are some of these claims that they are representative or that they are complete, but there are also strong selection biases in these samples. So the D-sharp survey selected all the targets that had a bright millimeter flux and that were already previously resolved with ALMA. So you have very weird selection there. You have not just the flux threshold, but also previous people have already observed that. In Ophiuchus, there's this survey where they did kind of the same thing. They selected only the brightest disk to follow up from their initial survey to follow up with high resolution. And Long et al. Selected targets in Taurus. And so she selected all the disks without making that brightness detection limit. But she did limit herself to spectral types earlier than N3. So basically the A, F, G, K stars, and an M1 and M2 stars, but nothing of M3 and further, basically the lowest mass stars. So in that way, the sample is biased as well. So in this review paper, they try to visualize this detection bias and the detectability of substructures. So they said, well, you have disks that are well resolved, they're green, so this size divided by the resolution is larger than 10. You have somewhat resolved, the blue dots, and you have barely resolved, so the red data points. And then they say this is with substructure and without substructure. So they try to say something about how often substructure is detected, but they essentially conclude as well that the detectability depends so much on the resolution that it's really hard to say anything about statistics. So for the lupus survey, we can only say something about the transition disk with large cavities. There, essentially, we have found 11 transition disks with cavities more than 50 AU in 68, so we have an occurrence rate of transition disk of 16% in a complete disk survey, so that's one number. Then in the Torres long survey that I was just mentioning, they find substructure, like gaps and rings, in a third of the sample, right? Actually half of the sample that were single stars, more binaries. But also here you had that selection bias of only relatively good stars. And then in the study where we essentially tried to combine disks from all nearby star-forming regions, we essentially distinguished between transition disks, ring disks, and also extended disks. So they probably also contain rings, separating them from the bulk of the compact disks here in black. And one thing that we noticed in this samples we have, like you can see that these colored disks, the disk with substructure, they're in minority, like about 15% of the total sample. But the reason why we think it's reasonable that you can separate them from the rest is because they evolve separately. And this is entirely based on the dust evolution argument that the disk with substructure are thought to have dust traps, so they maintain their dust mass, that's what we see. But the compact disks lose their dust mass all the time, and therefore that's essentially their distribution drops in dust mass. So occurrence is still hard to determine, but at least there seems to be some reasoning behind it, like why only a small fraction of disks have substructure. These are the ones that have dust traps that are maintained. So now for the same sample, we also looked at the dust mass as a function of stellar mass, which is, there's kind of a correlation in young, intermediate, and old, but also well scattered. But there's this sort of separate trend for the transition and ring disk, or the substructure disk. And there's something else that you may notice in this plot. And that is that most of these, I'm just going to say it now, that most of these transition and ring disks are located in this part of the plot, so around the higher mass stars. And so this is a very interesting phenomenon, because so what do we know about the IMF, about the initial mass function? Which types of stars are the most common? Exactly, low mass stars. So low mass stars, you can even see that in this plot, right? There are way more low mass stars than high mass stars. But we see most of the substructure in disks around high mass stars. So this is here just two examples of IMFs. So this is the stellar mass function in lupus, and here we have the Krupa and the Salpeter IMF function, and also the pre-stellar core mass function. All of those show that most of the majority of stars, the peak of the stellar mass distribution, is at around 0.2 solar masses. So if you observe more transition disk around, or substructure disk around higher mass stars, this is kind of enhanced by the fact that there are not so many high mass stars to begin with. So if you then look at the actual occurrence rates, here we use for transition disks. So this is the number of transition disks and the number of non-transition disks, product disks. it's kind of hard to see how they are different. But if we look at diffraction, there's very clearly a stellar mass dependence. So the transition around the high mass star, there are many more transition disks than around the low mass stars. But if we look at them as a function of age, the occurrence doesn't actually seem to change at all. And so this occurrence rate was also explored in this larger disk survey. Again, for transition disks as a function of stellar mass, it's kind of the same trend as before, but also for the ring and extended disk. Also here, there was this increase of occurrence when we look at different stellar masses. So this is finally a hint that, yeah, maybe not all stars have substructure, because there is a dependence on the stellar mass. It is not entirely about detectability. Well, then one more thing about detectability of the spirals in the near-infrared. This is a lot harder to say, like how many disks have spirals, because many stars have actually not been studied in scatter light imaging. So you need an AO system in order to do this kind of imaging, which means you only target the bright optical stars, not the stars that are that have high extinction, that are very dusty. However, in this review paper, they argue that even though they haven't covered, like their sample is not complete, they do cover a pretty wide range in both stellar mass and also in ages. So based on that, they say, well, at least we have a sort of a general view of what kind of things, what kind of structures can be present, but you cannot actually do a full occurrence. And then something else that was noticed for specific spiral disks, if we plot them in their stellar luminosity as a function of their gap width, is that most of the spirals are found in this corner of the plot. High luminosity and large gap width. And if we assume that a larger gap width is caused by more massive planets, and a higher luminosity results in a higher temperature of the disk, maybe that makes sense. That spirals are only detected if the disk is warm enough, so it's flared enough, and if the planet is massive enough to drive a significant spiral. However, since this plot, this sample is not complete, and this plot is definitely not properly sampled, you cannot really draw this conclusion right now. So, to summarize, substructures are often detected in bright disks, but it's very resolution dependent, and a lot of statements about their occurrence, you have to be careful. You really have to look at what have they actually chosen as their initial sample. Gaps can be related to planets, but there are still other possibilities as well, which doesn't rule out planets, it just there is an alternative. Spirals are seen in various wavelengths, and also their exact origin remains to be determined. So that's it for the substructure lecture. Are there any questions at this point?
I have a question about that last plot that showed us the gap radius.
Yeah.
Plus gap width.
Mm-hmm.
If you have for the same system, if you see more than one gap, which one are you plugging there?
I think so. These are mostly transition disks, but in case of the ring, I think I picked the inner gap. But I agree, it's a bit random. Yeah.
But that's where you would see the spiral structure.
Well, the spiral structure is visible usually throughout the disk, and it's always hard to determine what is the launching point of the spiral. Yeah. But the majority of the disks here are actually the disk with any other questions? Cool. Okay, so that's it for the lectures today. How far did you guys get with the tutorial? Okay, we managed to make some images. Continue online. Yes. Okay, I see everyone nodding. Okay, that's really good. Because that means that we can go to the fun part, and that is a new ALMA project. This is so it's a project that has been in the archive forever. I don't think the PI is going to publish it, but there's a lot of interesting disks in there: continuum data, line data, multi-wavelength for a large number of disks. And my idea was to kind of distribute the data, so you all have the data on your computer, but I have 14 projects, like all studying a slightly different aspect of these disks. And the idea is that you will start to make the images, like you have the measurement set that you don't have to do calibration anymore, you can start imaging, so same as in the tutorial. And then in the description there are a number of steps, number of analysis things that you can do, and also for the people that are fast, there are a number of bonus steps. Yeah, my idea is really that everyone just picks a project, work in pairs, and see how far you get. Make the images, play around with the different options of clean, really get familiar with cleaning and how these disks look like. Do some of the analysis, and then for Friday afternoon, prepare a few slides. This doesn't have to be like a nice presentation. This is more like, hey, this is what I've done in a few days' time with these data. And I do want to add, since these data are not published yet, if we find, basically if we all make a lot of progress, I would be happy to write a paper with all of you, like all of you included, where we present the interpretation of these disks. So I hope that will help a little bit of motivation. That is not meant as pressure. So it's meant, this project is meant for fun. It's meant to just get familiar with different data analysis. Yeah, I really picked these data because you cannot find it in a paper how the data are supposed to look like. You really have to figure it out yourself. And I hope this will you will enjoy it as well. Obviously I checked the data a little bit, but it's not like I've done all the steps that are in the project. So if there are issues and you can't figure it out, don't be afraid to ask me. Right? There could be issues with the data. There could be weird things in the data. I don't know. This is the fun thing about doing science. The best parts, the best moments in science are actually the moments where you're like, what the fuck is this? This was the case for Iris 48, I can tell you that. When we got that asymmetric dust trap, we had no idea what it was. And really our first thought was there's something wrong with the data reduction. So if you find something funny, let me know. But even if you don't, if we write a paper about this, it will be about all of the data altogether. So don't worry, you don't have to be the one who discovers something.